In this video, we're going to be taking a look at inputs to the computer and communication between computers on the vehicles. The first input, or the first sensor we're going to take a look at, is the thermistor, or temperature sensor. The first input that we're going to look at is temperature sensors. By far the most common temperature sensor is the thermistor, or an NTC, which is negative temperature coefficient thermistor. There are PTCs that are on the car. Those are used primarily for circuit protection, and those are located inside the computer. So even looking at a wiring diagram, you won't find that. We're only going to deal with NTC thermistors. Typical of engineers, if you find something that works one way, they got to change it around and make it work backwards. Normally, a device, if it is going to get hotter, its resistance will go up. Taking a look at this chart right here, this is one particular manufacturer, one sensor, one model year. Don't think this is typical of everyone that's out there. I mean, it's typical as far as changing resistance, but the resistance ranges for the temperatures will change. If you're working on a particular vehicle, you need to look it up for that vehicle. On this one, 100 degrees centigrade, we're at 177 ohms. At minus 40 is 100,700 ohms. If you unplug a sensor, the computer is going to show minus 40 degrees, and that's pretty well consistent throughout all the manufacturers, Asian, domestic, European. From minus 40 to minus 30 degrees, you look down here, we're almost 50,000 ohms difference. From 90 degrees centigrade to 100 degrees centigrade, we're only about 170 ohms difference. There's a larger resistance change in colder temperatures. This gives the computer more accurate monitoring of the temperature changes at colder temperatures. When dealing with engine performance or engine drivability, it is much more important that the computer see changes at the colder range in order to keep the timing accurate, the amount of fuel going in to keep the engine running correctly, and the emissions low. Once you get up above about 160, 170 degrees, the computer makes no more adjustments from temperature. Looking at this wiring diagram right here, here's our variable resistor, which this one is our NTC thermistor. Over here at the computer's going to put 5 volts on the circuit. There's a fixed resistor. The computer's going to monitor the voltage at this point right here. Wired in series through the thermistor and then to ground. You'll find most of the sensors on the computers do ground inside the computer. That's going to give it more accurate. If the ground begins to change for the computer, the ground will change for the sensors, so it has less of effect on it. If we're really cold, this is going to be a much higher resistance compared to this one, so we're going to have a higher voltage here. Minus 40 is equal to 5 volts. If we unplug the sensor, most all the computers out there will read minus 40 degrees. If you short these two wires together, the computer's going to see 0 volts. It's going to see whatever its max temperature is. On an air temp sensor, it's going to be 120, 140 degrees, somewhere in that range. On an engine coolant temp, it's going to be up closer in a range of 270 to even 310 degrees. You again would have to look it up if you're going to do that type of testing. NTC thermistors are a 2-wire sensor. 1 wire is ground, and the computer is monitoring the voltage right here. Depending upon the voltage, higher the voltage, the colder the temperature, within a range of 0 to 5 volts. If you're going to diagnose this, put the scan tool on there, look at the data parameter for that sensor, see if it's within range of it's supposed to be. The next sensor that you'll hear talked about for cars is an infrared temperature sensor. I have done a little bit of research, and I have not found any manufacturer that is using an infrared temperature sensor. I read one thing that said, okay, they're using it for monitoring the temperature of whether a person's there or not. I couldn't find that. What I did find is that as we move closer to autonomous vehicles, that these sensors will start being used in the front of the car to be able to look at a vehicle that's in front of it, even looking at road temperature, some other things. This is probably in the relatively near future that we will start having these sensors, but for now, as near as I can tell, they're not on the cars. Next sensor we're going to look at, or the next input, is going to be pressure sensors. On the left-hand side up here, you can see some of the places where we're using The TPMS, our tire pressure monitoring system. MAP is manifold absolute pressure. We also have barometers, or a barometric pressure sensor, fuel tank pressure sensors, a fuel line pressure sensor. We have AC high side pressure sensors, power steering, and then oil pressure, both the engine and transmission. That's a not exhaustive list, but it's a pretty good list of the different areas on the car where we're using the sensors. The technology inside of the different sensors changes. And on this right-hand column, you can see some of the different ones that they have on there, the strain gauge, Wheatstone bridge, piezoelectric. This is one of the times when I don't care about the technology that's inside of there. If you were checking a MAP sensor and it happened to be a strain gauge or a Wheatstone bridge, and you went to Napa and said, hey, I need a Wheatstone bridge, they're going to give you this funny look because they're not going to have any clue. You're going to tell them, I need a MAP sensor, make, model, and year. What we're going to be looking at is how are they wired, because that's where you're going to be doing your testing at. The TPMS, that's a standalone unit. It's inside the tire. If you want to communicate with it, you can do some communication from the car, looking at the dash or with the scan tool. The best way to do the diagnosing is get a TPMS tool that you can hold up to the tire and you can communicate with it. You can get its identification code, you can get the temperature inside there, you can get the pressure inside there, and it'll give you an idea of battery life, good or bad. On the MAP sensor, this is the one that's behind me here. We're going to look at this one on the left-hand side, and what you're going to see is 5 volts are going to be applied to the sensor. What you will find is most all sensors on the vehicle operate within a range of 0 to 5 volts. They're 3-wire sensors. Reference is going to be 5 volts. Ground, which you need to make sure it's a good ground, and then our signal. From our MAP signal, if key on engine off, put the scan tool on there, you should see about 4.5 volts. The higher the altitude, the lower the voltage is going to be. Start the car up, you should see between 0.5 and 1.2 volts with the engine running. When you go to diagnose it, if there's a code for the sensor, this MAP sensor, which is dealing with manifold pressure, is going to react to what's running on the car. If the engine's not running right, that can set a MAP sensor code and there's nothing wrong with the sensor. You need to check base engine first, make sure the engine is running good. Next, if this doesn't plug right into the manifold like this one would down here, there's going to be a vacuum line. Got to make sure that there's nothing plugged in the vacuum line or the vacuum line hasn't collapsed or anything like that. Check your base problems first before you go looking at the sensor. If it's connected up to the manifold good, has a good 5 volt reference, good signal, but the output is not correct, time for a new MAP sensor. Same thing would go with the fuel tank pressure sensor. In fact, this right here could be either a fuel tank pressure sensor or a MAP sensor. They pretty much look the same. AC pressure sensor is going to look more like this, but again, it's going to be a 3-wire sensor. When you get to the oil pressure, looking at this one down here, this is going to be 2-wire, but where it screws in is its own ground, so there is no wire there. It's going to look like a single wire. I'm going to unplug this wire right here at the sensor. The reason I'm going to do that is because if this gauge isn't working correctly, and the other gauges on the car are, it's either going to be this gauge is faulty, the wiring's faulty, or the sending unit's faulty. The sending unit lives in the harshest environment. It's the most likely to fail. I'm going to unplug this tan wire, key on, this gauge should read all the way down to 0. Next, I'm going to ground this wire down here, and the gauge should read all the way up max pressure. If it does, the gauge is good, the wire is good, it means my oil pressure sending unit is bad. A real quick, easy test, if you're not having an accurate reading, what you have to be careful on today's vehicles is the manufacturers have switched over to using a high volume, low pressure pump on the engine. And what some of them are saying is that, man, 4 psi or 7 psi, that's just fine for the engine. It will live no problem with pressure that low. If you get a customer brings their vehicle in and they're talking about low oil pressure, you need to check the oil pressure, put a mechanical gauge on there, look at the spec, make sure that there really is a problem before you go to try to diagnose it. Next, we're going to look at motion sensors. First one we're going to look at is a potentiometer. A potentiometer will monitor a limited range of motion. Where we're looking at rotational, it's going to monitor about a 90 degree. Your throttle is going to open about 90 degrees from fully closed to fully open. Potentiometer does great for that. I have seen potentiometers on seats. When you have a memory seat function, I've seen it on the steering column. They are located in multiple places. A short list here, the throttle position sensor, which is this one right here. So the computer can know what position you've requested with the throttle. When you get to your drive-by-wire systems, your accelerator pedal position, that's this piece right here, will have at least 2 potentiometers in it. The mode door, which is this here, has a reversible DC motor. That's 2 of your wires. The other 3 terminals are for a potentiometer. So the computer knows what position that door is in, knows which direction to move it. There's going to be potentiometers all over the car. You need to understand this one. Many fuel tank sending units are potentiometers. And they also have another technology that they're using, which is a Hall effect sensor. You got to be careful with the name Hall effect because they have a Hall effect switch, which will create a digital signal. This Hall effect sensor is relatively new, but will create an analog signal the same as the potentiometer will. Different technology inside, but for testing purposes, you can test it the same. Looking down here, you see the 5-volt reference. It's actually the same 5-volt reference as the map sensor, evaporator temperature. It's used for a number of different sensors. We have 5 volts coming out. This shows you a resistor right here. This resistor is not actually part of the circuit. There's going to be 5 volts right here. What this is for is if this wire accidentally got shorted to ground, it protects the 5-volt generator inside of the computer. 5 volts at terminal A, ground at terminal B, C is our signal. There's a resistive strip for this fixed resistor here. This arrow is actually a contact that slides back and forth across that resistive strip. Typical closed throttle, you're going to be around 0.5 volt, wide open throttle around 4.5 volts. For testing, this sensor, like many of the sensors on the car, the best way for testing it, if you suspect that you have a problem with it, put a lab scope on there. Here's 0 volts, one range of our travel, 5 volts, which is the other range, which typically you're going to not see it go to the full 0 and full 5 volts. As you slowly move it through its range of travel, you want to see a nice linear change. The little bit of a wow that you see right there is because this one had some resistance to it, so it didn't want to move and moved easy, and so I didn't get quite a clean line coming through there. This is okay. This is a result of how I turned it. What you don't want to see is if the voltage suddenly dropped down in a spot like that. That shows you there's a glitch or a bad spot in there. When you see that, time to replace the sensor. Next one we're going to look at is a PMG, or permanent magnet generator. Pickup coil is the name that I learned it, working for GM. Magnetic pulse generator, there's a lot of different names. I like the PMG best. It's the most common name that I hear out there. It also best describes how it's going to work. This will monitor rotational movement. Crank sensor, cam sensor, wheel speed sensor, vehicle speed sensors, things that we're going to be rotating. This is by far the least expensive sensor that's out there, and it works good. Take a look down here at the bottom. This part right here is going to be a magnet. Where they show just 2 strands of wire, there's actually going to be 1,000 or more strands of wire across there. Both ends of that wire hook up to the computer. One side's going to go to ground, the other side the computer's monitoring the voltage. Looking up here at this pattern, we're going to start at this spot right here, and what we're looking at is one of these teeth is coming up to line up with this magnet. Air has a high reluctance for a magnetic field. This ring has a high permeability, meaning the magnetic field can go easily through that ring, has a hard time going through the air. As that tooth moves closer to it, the magnetic field is going to expand out. As the magnetic field spans out, it is going to induce a positive voltage in there. When you get to this spot right here, that means that tooth is exactly lined up. The magnetic field is now expanded out as far as it's going to get. As the tooth moves away, the magnetic field is going to collapse down. That's where we're going to get our negative voltage. Positive voltage, tooth is moving closer to it, lines up, goes to 0, tooth moves away, we get our negative voltage. Anytime you use a magnet to generate electricity, you're going to generate AC voltage. Again, the best way to check these sensors, if you have a DTC for one of these sensors, put a lab scope on there. Lab scope's going to update really quick. It's going to give you a nice picture of what's going on. If you put a multimeter on there, you can read the AC voltage, but it'll skip a glitch. You won't see if a tooth is missing or damaged. If you look at frequency, it'll give you the frequency. However, the computer looks at two different things. The computer looks at the frequency, but it also looks at the amplitude. How high are these going? Faster it spins, the greater the voltage is going to produce. And the computer is looking to see that these are consistent. If somebody got in there and pried against this and flattened down some of these teeth, that is going to cause this voltage to drop down like that. The signal would drop down on both sides because that tooth is not as close. That's going to set a code. If you put the scan tool on there, you will see a signal from that sensor. It's going to give you a speed reading for the crank, cam, wheel, whatever it's monitoring, but it still sets a code. The lab scope will show you if there's a problem like that. Next one for monitoring rotational speed. This is a Hall effect switch. There is also another technology completely different from a Hall effect switch that is an optical sensor. These will generate a DC voltage or a digital signal. Looking right here, I deleted what was inside of here because I don't care about the technology at this point right now. If my crank sensor is bad, then I need to go get a new crank sensor. Whether this is an optical sensor or a Hall effect, it doesn't matter. The testing of it is going to be exactly the same. With a PMG, going back to this last slide, you're going to identify a PMG by two wires. You're going to identify a Hall effect switch or an optical. It is going to have 3 or 4 wires. First of all, reference low, that's our ground. Pin C is going to be ground. We need to make sure that we have a good ground to our circuit. Pin D, this one says 10 volts. You want to make sure you have at least 9 volts coming to this wire. You will find them that they're battery voltage. It needs at least 9 volts. I was looking at a Chrysler schematic, and Chrysler said that this was 8 volts. And I was thinking, oh no, I've been lying to people all these years. When we went and tested it, it's battery voltage on the Chrysler. The reason that they said it's 8 volts is because Chrysler uses an 8-volt square wave. Power, ground. All Hall effect and optical sensors have to have a power and a ground. Power, at least 9 volts, a good, clean ground. So no more than a 50 millivolt drop across the ground. This is a 4-wire sensor, meaning it has 2 outputs. Looking up here, this is the output from this particular sensor. It has a 3x reference, so each time the crankshaft goes around 1 complete revolution, it has 3 signals. You see the signals are different sizes. That's how the computer is going to know which 2 cylinders are coming up TDC. This one is an 18x reference, or a high resolution. This is going to allow the computer to have precise control of the timing. It is also going to allow the computer to detect a misfire. As a spark plug fires, the piston should speed up as it's going from top dead center and then slow down as it gets closer to bottom dead center. The computer can watch this from this high resolution sensor and be able to detect a misfire. There's your Hall effect optical sensor, either 3 or 4 wires, power, ground, 1 or 2 signal wires. Check your signal wire with the lab scope. If you put a voltmeter on there, this voltmeter is going to read 2.5 volts. So this one is a 5 volt square wave. This would read just a steady 2.5 volts, but you wouldn't know if there was 2.5 volts on there or 5 volts alternating. If you went to frequency, yes, you would see a frequency signal, but if this ground were bad and only coming down to 1 volt or 3/4 of a volt, it's still going to give you a frequency signal on a voltmeter. Put a lab scope on there. If the signal's good, you're done with the diagnosis. That part's good. If there's no signal or the signal doesn't look good, check power and ground. If there's good power and ground but the output's not good, replace the sensor. Now we start getting much more complicated with our motion sensor. But before we get complicated, let's look at the simple one. This is a sensor that was used with the first generation airbags. It had a magnet here which held this steel ball in place. And then there was these contacts here. They had a real thin plating of gold, and these were gold contacts. They wanted to make sure no corrosion was going to happen in here. When you get in an accident of sufficient force, that is 15 miles an hour or greater, into an immovable object, the momentum of the vehicle coming to a stop is going to allow this steel ball to overcome the pull of the magnetic field to move forward and touch these two contacts. There will be at least 3 of these sensors on those early systems, typically 1 for power, 2 for ground. If the power one and 1 of the ground one moves forward and closes these contacts, that would deploy the airbag. This is a motion sensor, but really low tech. They were really low tech, but they are specific for the vehicle. How much weight is the vehicle? How large is the crush zone in front of the vehicle? Where is this located on the vehicle? That would determine what size magnet they'd use, what size steel ball that they would use, how far the steel ball was from there, or the amount of G-force to make it move forward. We've now gotten much more complicated, and we're going to look at the airplane. We have 3 different angles on here. Our pitch, yaw, and roll. Pitch has to do with nose down or nose up. This is on the airplane, but if you slam the brakes on a car, it's going to nose down. As you accelerate, it's going to nose up. We have pitch on the vehicle. The yaw is when you're making a turn. Make a hard turn or a left turn, and things want to slide across the seat. That's our yaw. And then the roll is, especially with a soft suspension on a vehicle, as you make a turn, the weight of the vehicle gets thrown to the outside. We have 3 different angles: yaw, pitch, and roll. There is a sensor that is mounted inside of the computer, at least all the ones that I've seen so far, that is monitoring these 3 angles. This one computer is going to communicate with other computers on the car to be able to control that vehicle and keep it under control. For example, you're driving along, you're doing a relatively fast speed, and you all of a sudden crank that wheel over to the right, and you slam on the gas because you want to feel that back end slide out. You want to do some drifting. That computer is going to look at the vehicle speed. It's going to look at the yaw that's on there. It's going to look at how much the vehicle's rolling, and you slam your foot down the accelerator, and the computer is going to say, nope, it is not going to accelerate. It's not going to allow you to bring that back of the vehicle out of control. If you started to panic because somebody suddenly pulled in front of you and you slam on the brakes, the computer's going to look at this. It's going to put more pressure to the outside wheels because the car's leaning over that way, less pressure on the inside. The computer's going to adjust this. If you have a full active suspension system, the computer can actually pump up the shocks on the outside, drop down the pressure on the inside, and literally make the car lean into the turn. All of this has now become federally mandated. They are doing everything they can to try to keep you from doing something dumb with the car and trying to keep that car under control. When you start doing customizing to the vehicle, such as suspension changes, tire size changes, all of that is going to affect this. It means it's not going to work the way it was designed to work. If you get a code with these sensors, it's most likely going to be replace the computer because everything's inside of that housing. We have photodiodes, phototransistors. When we talk about photocell, it's going to be one of those technologies. There may be some other technologies that are used, but what we're going to end up with is a variable voltage signal depending on the amount of light that it's exposed to. This one is showing you a photodiode. This diode is going to change resistance or change a voltage drop across it depending on the amount of ambient light that it's exposed to. On the car, where you're going to see this most common is up on the dashboard, typically toward the center. We're going to use it for 2 different systems. One is our automatic headlight system. It begins to become dusk. We're going to turn the lights on. If it's bright outside, we'll keep the lights off. You can identify vehicles that have this sensor on there when you see them go into a tunnel or under a bridge and they get stopped there. After the car's been there for a little while, lights come on. When they come back out in the sunlight, you'll see it'll take up to a minute before they turn the lights back off. The reason they've got the delay built in there is because if you're driving at night and you come to a stop under a street light, you don't want to turn the lights off on the car. Purposely have that delay built in there. The other thing that it's used for is a sun load sensor. This is with your HVAC system on your automatic temperature control. An example of this, I was driving a Buick Roadmaster through eastern Washington. Outside temperature was 68 degrees. I had requested 72 degrees inside the car, and the computer turned the air conditioner on. I was heading east. It was morning, the sun shining in through the windshield. Now the windshield on this car is about the size of a twin mattress. It's a big car, big windshield. Because the sun's out there in front of me, the sun is putting a lot of heat into the vehicle through the windshield. That sun load sensor looks at how bright it is, and the computer is going to compensate for the amount of heat that the sun is going to put inside the vehicle. And it did that. I turned the AC on, even though I wanted it warmer inside the car than it was outside. The simplest of our inputs that we're going to be looking at is a switch input. This can be that the computer monitors a circuit that it's not controlling. For example, if you had an alarm system, you had an older vehicle that you open the door, the interior lights turn on, you close the door, the interior lights shut off. There's a switch on the door. The computer monitors that switch. It sees either voltage high or voltage low, depending if it's ground side controlled or not. When you open the door, the switch changes, the computer sees that happens. It's either open or closed, on or off, however you want to look at it, voltage high, voltage low. This one over here, again, is a switch input, but this one gets a bit more complicated. Battery voltage right here at the top. This wire goes into the computer, and there's a fixed resistor in the computers after this wire here, so the computer is going to monitor the voltage on this wire before that last fixed resistor. Depending on which one of these switches closes, it'll change the voltage drop across the circuit. Computer sees 0 volts, no switch is pressed. When you hit one of these switches, the computer sees what the voltage is, so it knows which switch is closed. You could have dozens of these switches with dozens of different resistors, and the computer would see the voltage drop. On some of the more complicated ones, you can have 2 switches closed, and the computer would be able to identify that. Another term when dealing with your inputs to the computer, and this is going to be a feedback system, also referred to as closed loop. But I want you to register in your mind, write it down, get a tattoo, whichever you need to do to be able to remember this. When you hear the term feedback or closed loop, that is a computer monitors its own output. Heater at your home is most likely one of these systems. Computer is controlling the temperature of the room, and it's monitoring the temperature of the room. That's feedback. Few places that you will typically find that. We already talked about the mode door, a reversible DC motor. Computer needs to know what position the door is in so it knows when to move it. There's a potentiometer built inside of here. This one here is an EGR valve, or exhaust gas recirculation. This is a large solenoid. That's what you're looking at right here. That is the solenoid. The dotted line that comes over here to this potentiometer. There's 5 terminals on here. 2 are for the solenoid. And then there's going to be power, ground for your potentiometer, and here's the signal. Computer commands the solenoid open 25%. The potentiometer says, hey, you're 28%. Computer's going to change the duty cycle until it gets the valve open exactly as far as it wants. The most common place you're going to hear the closed loop term is with the heated O2 sensor. Some people get really hung up and they think closed loop O2 sensor. Remember, closed loop or feedback is a computer monitors an own output. We have that happening on multiple places in the car. Here's your heated. O2 sensors start working about 600, 700 degrees, so we need to heat them up to keep them working. And it's a variable voltage signal that is going to produce. Computer is going to control how much fuel. The O2 sensor is going to tell it too rich, too lean, or just right, and the computer will adjust the fuel based on that. Closed loop feedback. Communication. So if you're following along in the book, this is going to be changing the chapter on our communication with the vehicle. First manufacturer to put a digital computer was GM back in about 78, 79. Chrysler had a computer in their car. Ford had a computer in their car. Bosch had a computer in their vehicles. And Ford and Bosch were already selling those computers to other manufacturers. I remember looking at a 75 Cadillac that had the 5.7 liter V8 with a Bosch fuel injection system. Then in 78, 79, GM puts a computer in, so 4 or 5 years later, and GM claims to be the first manufacturer to put a computer in. Well, what I found out later was that Ford, Chrysler, and Bosch were using analog computers. Capacitors, resistors, very slow, temperamental, temperature changes they didn't handle very well. GM was the first manufacturer to put a digital computer in. The other thing that GM did that no other manufacturer had done yet, and that is the computer could talk. Computer couldn't listen, it could only talk. What you're looking at here, here's your check engine light or service engine soon light, and it was tied in with this pin 39411, which went to your diagnostic connector. The computer would turn this light on and off, and that was your bits, which 8 bits make a byte, which is 1 character. And this had a baud rate, or the speed, of 80 bits per second, which means 10 characters per second. Extremely slow. If you were going to download even a low resolution movie at this, it would probably be downloading for a month before you'd be able to watch it. Extremely slow. They came out a year or two later with their next generation, which was 160-bit. They double the speed, but still, it's extremely slow. The engineers, as far as they were concerned, this was assembly line diagnostic link or assembly line communication link. They wanted that thing removed at the end of the assembly line. Car would come to the end of the assembly line, they'd put a cheap scan tool on there, they would look at it, hey, there's no codes, data looks okay, take that thing off. Taking it off was an extra expense, so okay, just leave it on there. The repair side of the industry is looking at this, hey, we could use this to diagnose, and then the legal side is going, hey, people are going to be able to reprogram it. It's like, no, you can't reprogram from this. This is talk only. We ended up with scan tools because of this. By 84, so we're looking at about 6 years later, 5, 6 years later, now we're getting systems that are usable. They're bidirectional, meaning you can talk to the computer and listen to the computer. For you, if you've ever put a scan tool on and commanded codes to clear, that was bidirectional. First one we'll look at is GM's UART system, which was Universal Asynchronous Receive and Transmit. Here's our IPC, or instrument cluster. Looking at this tan wire, comes to the DERM, Diagnostic Energy Reserve Module, which was your airbag. Came to the assembly line diagnostic link, then went to the electronic brake traction control module, then went to the air conditioner program, then went to the powertrain control module, and then back here. Now, this looks like there's 2 terminals for communication, but there's actually only one for communication. If you look at this, you'll see it's a loop. This was considered high fault tolerance. If this wire broke right here, communication from here could go this direction, communication from this one could go that direction. A single break in the wire on this system, you would never know the wire is broken, communication would happen no problem. Protocol for communication required a master and slave. The IPC was master. None of these computers could speak unless the master gave it permission to. So you start the car up, the IPC has adjourned. Have anything to say? No. EPTCM, anything to say? ACP, PCM, yeah, I've got a DTC set, turn on the service engine soon light. And the IPC would turn the light on. Master, slave, controller communication. The data is now 8194 or 8,000 bits per second, which is way faster than it was before, but home technology, nowhere close, but we didn't need it that way. Chrysler had their CCD, or Chrysler Collision Detection. They were 7812 bits per second for their baud rate, but they used 2 wires for communication. We're looking at this gray and lavender here. Here's our PCM. Down here was the transmission control module, and you see they're tied together. Instrument cluster, overhead console was another computer, body computer, airbag computer, and then coming over here was our diagnostic link. There's your computers connected up on there. Chrysler's collision detection had no master, no slave. What they would do is it would sit there and be silent. If 2 computers decided to communicate at the same time, they would both detect that there's another computer talking, they would both stop, and there was a timer built into each computer with varying amounts of time. The highest priority computer had the shortest timer. Whichever one timer ran out first, Then it would start talking. When it was done, the next computer would talk. That's actually the same protocol that's used on the internet. When you connect up your phone or a computer, there's no master, there's no slave, just whoever wants to talk. And if somebody else is talking, they wait. By mid-'80s, all the manufacturers were going with a bidirectional communication using various technologies. Bosch came out with what is arguably the best system that's around, called Controller Area Network. On the Controller Area Network, they will come with various speeds. Bosch did something really strange, and that is they gave this technology away. Whoever wants to use it can. Where Bosch makes their money is technical support. You've got a ABS controller from Tevis. You have your engine computer. Those need to talk together. You're going to use the CAN technology. You can either pay 2 teams of engineers and try to figure out, or you can hire the engineers from Bosch who have been doing this for years. They can do it a lot quicker, save you a lot of money. In the mid-2000s, the federal government came through looking at our emission control system and required everybody has to go to CAN. You're going to be dealing with CAN. European cars, all using the CAN network. Domestic cars, Asian cars have all switched over to using the CAN network. On the cars today, we have dozens or more computers that are on the vehicle. They all communicate, but not all on the same network. You will have multiple different communication networks on the car, some fast, some slow. If you have an engine computer and an ABS computer and you're going to do traction control by applying the brakes, the communication between those two computers has to be near live time. That's going to be a very fast network. For the switch to control the window, so I've got a switch to move the window up and down over on the passenger side. If it takes 200 milliseconds for the window to start to move, who cares? That's going to be a slow network. Bottom line for fault tolerance, the faster your communication, the less fault tolerant it's going to be. Here's what makes CAN so good. They're using 2 wires. This shows they're both at 2.5. There's actually a little bit of voltage difference between these two. With the voltage high, or with the CAN high, it's going to go from about 2.5 up to 3.5 volts. The other communications were using like 3.3 volts or 3 volts or some other voltage, and it's going from 0 volts, 3.3 volts, which means you have no magnetic field. The magnetic field expands out, collapses down each time you go to say something. Well, that magnetic field is going to induce a voltage into any conductors that are close to it. That includes on the motherboard in the computer. EMI was a huge problem. Bosch solved that problem by only changing just about 1 volt. And you'll see that they don't switch it, they ramp it, which means the magnetic field is going to move very little and it's going to move relatively slow. EMI is almost gone. By moving this 1 volt and this 1 volt, we have 2 volts difference, and then back down here. So this would be your 0, this would be your 1 as the communication goes through. Over here is our DLC, or data link connector. All vehicles sold in the United States since 1996 have this connector. Most all of them, like 99 and 44 100ths of them, under the dash driver's side. Pin 6 is CAN high, pin 14 is CAN low. If you want to check the communication, take a 2-channel ADScope, ground at pin 5. Pin 5 is your signal ground. Kind of missed on my circle there. Channel 1 on 6, channel 2 on 14. Adjust your volts per division, your time per division until you can see this happening. If you were to see the CAN low go down like that, but CAN high went straight across like that, that means you've lost half your communication. And now you know that the problem is on your CAN high side of the circuit. Looking back up at this last one, this is off a late 2000 Land Rover. ABS module, transfer case control module, engine computer, AFS, I'm not even sure what that one is, transmission control module, diagnostic socket, module for the steering column, steering wheel sensor, instrument cluster, switch pack, center console, seat occupancy, restraint control. These are both part of your airbag system. Center console, module for the seat. All of these computers are all on the same communication network. This junction box that's up here, if you were to find that, it looks like a connector, has a whole bunch of the same color wires and just a cap over the top of it. If you were to open that cap up, you would see that there's a shorting bar. All those wires are connected together. Every one of these computers that's on there, that wire goes out to it. If you get a little bit of resistance inside there, so some corrosion started growing inside there, it's going to take down the communication. None of these computers can talk with one another. You have to try to figure out what's going on. Here's where you're going to find out first, is looking at your communication here, see which line went down, or both of them went down. Now you got some catastrophic going on. If there's only one computer that won't talk, you're looking at that computer problem, not the rest of the network problem. There are classes that they will offer that go through CAN communication. I think for the most part, those classes aren't that critical, because if I have a CAN problem or a communication problem, here's where I'm going to start. Pin 6 and 14, lab scope, I'm going to look to see what's happening. If the communication is happening, hey, everything's good. I need to find out, okay, which computer went down, looking at DTCs and the like. If there's no communication on one or the other, now I know where to start my diagnosis. I'm going to start by unplugging the computers one at a time. When my communication comes back, that's the computer that took down the communication. That computer needs to be replaced. If it still doesn't work when I've unplugged those computers one at a time, now I need to start inspecting the wiring and find out where the problem is. So like at that junction box where there was some corrosion I talked about earlier. When Washington State was doing their emission testing, a lot of vehicles failed the emission test because of no communication. Most common problem, pin 16, which has nothing whatsoever to do with communication. But for some reason, that network, the CAN network that the PCM talks on, if there's no power on pin 16, it won't talk. First thing to check, if you have a no communication, pin 16. Pull the penny out of the cigarette lighter, replace the fuse that got blown. Most of the time that fixed the communication problem. Pin 6 and 14 are communication, pin 4 and 5 are ground. On a CAN system, 5 pins to check. Check pin 16 first, make sure there's power there. Pins 4 and 5, make sure those are good ground. Again, a 50 millivolt drop across those grounds. Then, look, check your CAN high, CAN low with a lab scope. Check to see if the communication is happening. Second to last communication, this one, probably you're going to never deal with this one. Not very many manufacturers are using this media-oriented system transport, or most. What this is fiber optic. With the telephone system, they're using a lot of fiber optic. It's amazing if you did some research on what's going on with that. First of all, fiber optic, looking at this image down here, you can see that the light is being transmitted through these fibers. This is for decoration, for show. They've had this around for decades. We can put an LED at one end. You can blink the LED on and off. You put a phototransistor at the other end to turn on and off in reaction to the light, and you have communication. There's your binary. This right here, this is the fiber optic from out of a Volkswagen, Porsche, Audi, one of those. Typically, if a car does have a fiber optic, it's going to be a single fiber optic that runs just about the length of the car. It's going to be a computer in the front communicating with the computer in the back. It's bidirectional communication. If this cable is damaged at all, you replace it. There's no repair to that. The advantage to fiber optic, light is faster than electricity. 2, EMI will have zero effect on a fiber optic. Get more secure communication that way. It is a good way to communicate with the fiber optic. However, almost none of it on the car. Just an occasional car will have just a single one. Check the physical condition of this fiber optic. If it's in good condition, you got to figure out which computer is not communicating on there. Oh. And I don't know what happened to my slide. Okay, we'll just talk about it. On the last one is our wireless. When you go to buy new vehicles, They have the wireless phone technology in there. They want you to subscribe to that. So now you can make phone calls from your car just by talking to it. They will have, some of them, satellite communication. And again, they want you to subscribe to that so you can communicate with their operators. Check engine light comes on and they can look at the condition of the car. This is used by police. If you have this system and your car gets stolen, they can actually command your car to shut off. So the police will sit there and watch it. It gets to a place where it's safe and okay, and the car shuts down. They have those type of communications. They also have Wi-Fi. So they'll have a hotspot inside the vehicle. Again, it's wireless communication. Then the other one they'll have is Bluetooth technology. And that one we actually already talked about with our TPMS. Bluetooth has about a 10-meter range. So we have wireless communication happening within the car. That will also need to be diagnosed. So hope that helps you.